but the introduction will contain something about dimensionality, cellular automaton, as I said, so hardware parallelism, so we're going to be using GPUs, and a little bit about the API, because CADDIES is not just a flood model. I'll touch on that a bit later. One of the big parts of CADDIES and the flood model is the trained data, ESM, DTM, and DM, so I'll touch on that. There's various rule sets in CADDIES. As I say, it's not just one flood model, it's an API. So I'll touch on the ranked rule and the weighted rule. And then we will look at the CA flood application, which is the actual model that uses the API and the rules. And then a few test cases just to give you a few examples of how the actual flood application works. So CADDIES was a EPSRC funded project back in 2010 to 2013. I think we actually got a bit of an extension on it. So my PhD was genetically evolving these rules, and I helped to develop the system. So it wasn't just myself that did it. There was a team of us, so some of us are still here, aren't they? So yes, dimensionality. There are fully 3D models which will take the particles and they can move in any direction, but this is very complicated, so it takes a very long time to run. Down at the other end of the scale, we have 1D models. So we either think of the rolling ball technique for something like pipe burst, where you choose one route for the flood path, or you're thinking of 1D pipe networks. Now these are the other end of the scale, so they're very, very fast, but they're not as accurate as we'd like. So CADDIES sits somewhere in the middle as a 2D or 2.5D model if you're thinking about the surface elevation here. So you can almost think of that as a 3D object, but you've only got elevations on each of the 2 dimensions, so you can't handle things like bridges, which have 2 elevations. So it's designed to be super fast because it's based on the cellular automaton model. And that is, cells are the grid cells, effectively. And we use a local neighborhood, so the von Neumann neighborhood, which is north, south, east, and west. As I say, we have a terrain level inside each cell, and then sitting on top of that, you have the water depth. And if you combine the two, we call that the water level. And as I say, we take the local neighborhood and effectively calculate the next state for each cell. And that's based on the original concept of cellular automaton, which was created in the 1950s and 1970s, the first one being the game of life. It's a very, very simple rule set. It's a discrete set of cells, and it's only binary, so on or off. But the revelation was that it can create these very, very complex patterns from the interaction of many simple parts. And it can be calculated in parallel, which means we can use our new parallel hardwares to make it go even faster. CADDIES can either use a square or hexagonal, it's slightly experimental at the moment, but possibly other types of grids as well. It has a continuous state, so these are still discrete because they are a floating point, but it is a scale of the levels. As I say, using a von Neumann neighborhood, and we can do it in parallel both on the CPU and on GPU, general purpose graphics card, which is why it's GPU. And we're using the weighted rule as the best rule we have at the moment. So the idea is that, well, not everybody will have a supercomputer or have access to one, but all modern computers are equipped parallel. It's not just the CPU, which we called multi-core, because you only have possibly 2 to 12 cores, so it's not many cores, but they can work very independently. Whereas the GPU is called many-core. We're talking of thousands of cores, but they have to be doing something very similar to take advantage of that hardware. Just to visualize that, we have many, many thousands, and we basically run a thread in each cell, rather than running just a few threads. To say, CADDIES itself is not the actual flow application, it is an API. So it's designed to take a model, and that will plug in through the API, the application programming interface, into the implementation. And that is effectively a black box as far as the rule is concerned. So the idea being, that could be a square grid on the CPU or a square grid on the GPU, or it could be something completely different, like a hex grid on the GPU, just as an example, because we have only implemented that on the CPU thus far. But either way, the rule will still follow the same code. So the idea is that we can test the different rules in the same framework. That was the original idea, to compare, because there are many different models out there. Later on in some of the test cases, I will show you a few of them for comparison. As I say, we can have various different grid types that are possible. We have not implemented all of these yet, but we have implemented square on both the CPU and the GPU, and we have an experimental hexagonal grid. It would be possible to do triangular meshes, either regular or irregular. Possibly octagonal as well, but as I mentioned to a speaker earlier, how do we consider the flow to a diagonal cell, as there is, how much width would that flow pass through? Could possibly be a point which would not work very well. This is going to take a little while to explain. But we use the Manning's formula effectively, which is based on river. It is the river formula for calculating flow. So if we consider that a pair of cells is similar to a river. So we have 2 points where our terrain is sloped, and we will have perhaps higher water level than one, and then we will get a flow from one to the other, which is effectively downstream. So in each neighborhood, for each cell, we take each neighbor, and if it is lower, we can then calculate an outflow. So we do not calculate inflows at this stage, because that is an outflow from another cell. So once we have calculated the outflows for all cells, we have outflows in all what we call edge buffers, which is the area between a pair that a pair of cells shares. Then in a second stage, we go through all the cells, again, in a similar way, and then we simply remove an outflow and add an inflow. And because of inflow is also an outflow from another cell, that water should balance, unless we've got any going out of the terrain and we've got it open. Unlike the very first cellular tom-tom, which had an abstract sense of time and space, we have to actually assign a cell size. These have to cover a certain physical distance. And also the iteration, so going from one grid to the next grid, has to be a certain amount of time. Now given that, we will have a certain number of iterations of this to cover enough of our simulation time, let's say 2 hours for example, and we're doing 1 second every iteration. Will require quite a few iterations to do all that. In each iteration, you have to calculate every cell. So the complexity is the number of iterations times by the number of cells times by the complexity of each cell, basically. So that will tell you how long the computation will actually take, depending on your hardware, of course. So if you have faster hardware or more cores, it will go quicker, proportional to this. So later on, we'll cover a bit more on the complexity of the iterations, because we use an adaptive time step, so we don't move at a set 1 second or half a second each time. So it's very hard to actually predict ahead of time how long your processing time is going to take. Moving on to, as I say, the key part of this is the terrain data. Now in the UK, we do have an abundance of high resolution 1 meter data. This is mainly due to advances in drones and technology like this. Globally, there is 10 to 30 meter data available from satellites. But effectively, we need some sort of line system to fly over the terrain, zap some lasers down and determine the height from its position. From this, we can then get a field of points. Now, part of the problem is with things like trees and bushes, sometimes a beam will hit a leaf, sometimes it will miss them all and go down to the terrain. So we need to then use some algorithm to turn this field of points into a useful 2D terrain. As I say, we have different names for whether we are considering the top points or perhaps the bottom points. So it's a digital surface model for the actual top points, including trees, cars, buildings, people, whatever the laser is connected. And it's a digital terrain model when we have removed all those. Just to demonstrate this. So this is a pipe burst flood. So there is a single location where water has come out and then it is spreading. So this is slightly different from pluvial or fluvial. But you can clearly see in there, you can see buildings, obviously, but there are trees. I'm going to guess those are buses, and perhaps those are cars or people. So we either need to use an algorithm to smooth out the terrain or take the very lowest points from the field of points. And then if we use the DSM, sorry, the digital terrain model, I always get these two mixed up. Unfortunately, this has removed everything, so it's removed even the buildings. And these are critical to routing flow paths, basically. So what we need to do is use a hybrid. And in that case, we call it a DEM, digital elevation model. So what we can do is we can use a shapefile or something which identifies where the buildings are, and then we can use this mask to raise the terrain where buildings are present. We might do that to 3 meters or 5 meters to make them completely impassable, or we might do it to doorstep levels of 20 centimeters, 30 centimeters. In that case, we'd have to do something about the fact that buildings have walls as well. So this is what it looks like with the combined DM. This time we use 3 to 5 meters, so it's making the buildings completely impassable. So we can use 15 to 30 centimeters. And what we actually do is increase the roughness. I'll cover what roughness does later. Just to demonstrate this flood burst. So as I say, we have a number of rules that we developed in the CADDIES system. The first one in 2011, 2012 was the rank model, which uses a ranking technique based on the levels of the trains and the water levels inside the neighborhood. So this is a 2D representation of the von Neumann, the 5 cells in the von Neumann neighborhood. Its primary flood route uses the steepest slope. It still uses Manning's formula, but only on that steepest slope instead of in all 4 directions. So the idea is that this reduces the complexity of the local rule, which makes the entire complexity simpler, which makes it faster. So how that works is it takes the water in the main cell and then it starts distributing it to the lowest neighbor until that reaches the next neighbor. And then again, distributes some more of the water until it's filled up to the next neighbor, repeating the process along the ranking until it has distributed all of the water. And at that point, you know how much flow, you know how much volume, so you can calculate how much flow is going into each neighboring cell. Now that was the first rule, but it wasn't by no means perfect. It suffered from some problems of having too large of flows at the same time. And too large of flows in the von Neumann neighborhood can cause a huge oscillation. So if you have too much water go out of a cell into its neighbors, in the next iteration, too much water will come back into the main cell. And this begins again, and effectively you generate a checkerboard pattern which will destroy the quality of your simulation. And this is based critically on the time step. If you take a smaller time step, you are not moving as much flow. Our system uses this equation here to calculate the time step, which is effectively based on the cell size and the velocity at the time, and a relaxation parameter between 0 and 1. So this means we can turn it down. Other systems use a slightly more complex formula, but that would create more complexity in the actual model as well. This condition is called the Courant or Courant-Lindemeyer condition, which is supposed to be the condition at which oscillations will begin. And the idea of the second rule we came up with, which is called the weighted rule, is that it was going to limit the flows slightly in order to try and stop these oscillations, yet go at a larger time step, so take less iterations, so go faster. Yeah? This is at the cost of some accuracy, but we have minimized that cost of accuracy to a huge gain of speed. So the weighted rule, we had a first version and a second version. In the first version, we compute simply a weight between the main cell and each neighboring cell. And this is based on the difference between the water levels. So it's quite simple. So we see here 2, 2, 4, 5. That we can fix 13, 2 13s, 2 13s, 4 13s, 2 13s. And critically, this will leave some water in the main cell. So the idea is that it's not emptying the main cell, because if it's empty, clearly water must come back into it from its neighbors, which have received water in the previous iteration. This is designed to minimize the oscillation. So then we need to calculate the total amount of water that we're going to move. This is based on, there we go. So this is based on the water level difference of the smallest cell in the first version. So multiplied by the area, this gives us a volume of water. And then we can distribute that water based on the weights. And I'm going to cover a little bit on the second weighted version a bit later, as I'll show you with test cases why the first version didn't work very well. So as I say, we have CADDIES is an API, and we have a model, but we need an actual application to run that model. So we use the CA flood application, which uses the API and the weighted model. It is a terminal-based application, so it doesn't have any user interface. So we need to set up a text file to give it settings, and it will give you back some CSV files or ASCII terrain file, which I'll show you what that looks like there. And as I say, we can run that on a square grid on the CPU, either in serial, I'm not sure why you would, but you probably want to run it in parallel to get the most out of your CPU, or in parallel on the GPU. And we do have an experimental hexagonal grid, which is on the CPU in serial. So this is what the primary setup file looks like. It's just a simple text file with some settings in that will tell the program how to operate. And then this primary setup file links to a number of other files. So for example, a terrain file and some inputs and outputs. We're going to need to go through this in a little bit more detail because you are going to be using this system, hopefully. Just to go through it, we have a case name. The simulation name can have spaces in it. The short name is used in the output file, so it cannot have spaces in it. The version number you should not change. The model type tells us the model that we're going to use, and this one is the weighted CA2D version 2, which is the current model we have, so you should use that one. Then you need to tell it how much you want to simulate, 2 hours or 99 hours. This is done in seconds, so that is 20 hours, 3,600 seconds in an hour. We tend to start at 0, but you might want to start later for some reason. Once we've got how long we're going to simulate, we need to know the time step that we're going to use. And since, as I say earlier, we're going to use an adaptive time step, we need to know the minimum and the maximum. Generally, you leave those alone and let the adaptive time step adapt. And rather than adapting it at each and every iteration, because that's quite expensive computationally, we do that at every certain time interval. So every 60 seconds we will check the velocities, and if they are larger, we will reduce the time step. Conversely, if they're smaller, bigger. And our relaxation parameter, if you have that at 1, it would use the fastest velocities. That might not be completely safe. You still need a way to automatically derive this. And the maximum number of iterations, effectively, you just want to have that as large enough to cover enough iterations to do the simulation. So the next thing is roughness. Now this is the global roughness, so in every cell across the grid. It effectively tells you whether your water is running over glass or concrete or through reeds. So effectively it's going to make the flow slower those cells if you make it larger. Then we have some tolerances, so anything less than 0.001 meters. So it's 0.1 millimeter. It will not process any flow. Basically, surface tension will hold in place. This tolerance is for the output, so if there's anything below that, it will say there's no water in there. The slope tolerance is used in the time step calculation, because if there are very small slopes, ironically we would only use a small amount of water, but we usually need a very small time step to get that just right. So we waste a hell of a lot of computational power on doing not very much. So we cap that. And then we need a border condition at the edge of the drain or on any no data cells. So we could either have 1,000 or minus 1,000. So plus 1,000, nothing will get past that and be able to leave the drain. At minus 1,000, the water will be able to pour out to the sides. Then we need a terrain file name, which will link to another file which will have the terrain data in it. I'll show you one of those in a little while. Then we need some inputs. So we can have 3 types of inputs. Rain event, or an inflow, which is like a pipe burst from a single point, or water level event, which are used to simulate dam breaches, as the water from behind the dam replaces itself. Lastly, on this page, you have some outputs. So you have to tell it what outputs you want. Very lastly, there are some smaller settings, things like whether you want it to output some information to the terminal, and tell you how long it's taking, check the volumes. It's not really necessary because the system will balance the volumes. Of course, you probably want to remove the intermediary files. So the outputs that are possible, there's 2 main types of outputs that you can have. Point plots, which will take a certain location or set of locations on your grid, and then it will tell you that the water depth, water level, or the velocity at that or those points over the course of time. Location. So you can see here, this is how one of these output files looks. We've got an arbitrary name here, and then this tells you the physical parameters. So WD is water depth. We have a list of points. Each point is named, and then has an X and a Y coordinate, basically. And then you have a time interval to tell you how often to sample that from those points. The other type of output is a raster, so a grid of water depths, water levels, or velocities. Similar sort of setup file, so again you have an arbitrary name for this file, and then the physical parameters, so it's water depth in this case. And of course you can either have them at time intervals, or you could have the maximums in each cell. So you can have the peak here is true, and we've got them every 600 seconds as well. So that's the outputs. We also need some inputs. So say we've got 3 types of inputs. There's rain, so that will cover a certain area, and we will raise the water depth by a given rate in that area. And that uses a Pareto graph, whereas point source hydrograph. It's a linear interpolation rather than a stepped interpolation. And then I say water level or dam rates, where we raise the water level to the given point, allow that water to leave, and then we replace it back up to the specified level, because the water behind is replaceable. So a similar sort of setup here, with an arbitrary name. This one is actually a water level event. So we need to specify a zone, an area for that to be applied to, which is true for all three of them. So we even need to specify a point or a box. Then we have our hydro or hydrograph. So this is just a list of times and levels. And finally, we have our area. The top left x and the top left y coordinates, and then the width and the height of that area. So this is what a terrain file actually looks like, what an ASCII terrain file. So it's not the most data efficient storage system, but it is easy to read, is the idea. So we can have a quick look and see what's going on. So notice at the top there are some sort of setup parameters, and then effectively we have the grid of levels. That's it. So these are either space separated or comma separated. So these parameters, we have a number of rows and a number of columns. It specifies the size of your terrain. You want to make sure that that is the same as the number of actual data points you have in there. Then we have an x coordinate at the lower left corner and a y coordinate at the lower left corner. This isn't actually used by CADDIES, but it is used by GIS software to place your terrain. So if you're having multiple terrains, it tells where to put them. As I say, we also need to specify a cell size, how large are your cells. Finally, we say what our no data value is. So we have to make this an impossible to reach value, which is why we made it minus 9, and it's 9. And any cells with that value will then follow the border condition that we had earlier. So we can have an abstract shape of terrain if we like. And then we have our upgrade of data. That's the terrain file. So next we need to cover a bit about the time step. So I'll say that the time step adapts based on the cell size and the velocity. Of course, your cell size is not going to change during a simulation, but your velocities will. And your velocities will then affect the time step, which will then affect the complex system. You can see here some work I did on the pipe bursts. Basically, if you have a larger pipe burst, you want the flow to flow further, so limiting it to more damaging. To demonstrate that, so we've got a simulation of a pipe burst on here in yellow from InfoWorks, which is probably the industry standard for simulating models. Uses a triangular regular mesh. We'll try and get as similar as we can. And in blue, you can see our CADDIES model. So it is slightly different, but it's reasonably similar at this point. So on this setting, we've used a minimum time step of 0.01 seconds. And that means that it's taken us 5 minutes, 33 seconds to process this. If we alter that minimum time step and make it larger, with nearly half the amount of time to take us to process it. But as you can see, if I look back and forth a little bit, it limits the flow. So it's not quite gone as far. We can push this even further, of course, and make the time steps larger, which makes the processing time smaller, and smaller, and smaller, and smaller. But as you can probably begin to see, we're beginning to actually lose some of the realism. And we can push this right to the extremes, of course, where we're completely losing the realism, and it is not spreading far enough to be realistic. So you don't want to use a too high minimum time step. So InfoWorks uses an irregular triangular mesh, whereas all CADDIES implementations at the moment are regular grids. Now, on the CPU, CADDIES using its most accurate and slowest time steps is a bit slower than InfoWorks. But on the GPU, this is a different story, because so the GPU has many thousands of cores which need to be doing the very same thing. Whereas all these cells are slightly different. They might have different numbers of neighbors. So on the GPU, CADDIES is much faster on its slowest time step, on its most accurate time step. So we could go faster, as I just demonstrated, but we lose accuracy. And also, InfoWorks is cheating. It is using a single precision floating point value. So it's only a 32-bit value rather than a 64-bit value. Now I've done CADDIES on both a single and double precision to show how that's cheating, because basically when we use a single precision, we go twice as fast as when we use a double precision. So in other words, InfoWorks, if it used a double precision, it would take twice as long. So how to use the actual application itself. So we have two versions of the application, what we call CA Flood and CA Flood Pro. You can cover too much on the Pro application, other than the fact that that one has spatially variable roughness, rainfall, and infiltration. So in the basic version, those have to be set uniformly across the grid. So at the terminal, you call the application. You might have a .exe in the end. This is necessary to tell it to use the weighted model. So you have to put that in, basically. Then you need an input path to where those setup files are all located, so they all have to be in the same directory. And then you tell it the primary setup file. So in this one I call test1.csv. And then lastly, you tell it an output path, so where you want it to put all your files. It will also put the temporary files here. So if you've gone halfway through a run, you might have some temporary files in that location. You will want to delete them. So we have done some benchmark test cases. We've used not just InfoWorks, but UIN, which is effectively Albert's system, which is a fully hydraulic inertia 2D shallow water equation model. So the algorithm here is much slower, but it is considered accurate. So it makes a good benchmark to compare it to. So I'm going to go through a few cases just to show you what you can do with these. So this is an area called Keithley. So the VM here is 100,000 cells, 2-meter cell sizes, and we applied a rainfall rate, which is the equivalent of 1 in 100 year, for a duration of 60 minutes. You can see the outputs here, which is the maximum inundations. I'll show you lots of more video calls. You can see they are reasonably similar between UIM and this is actually the ranked model. So the reasonably good agreement seems to match up quite well. We have a number of points of interest that we looked at on that terrain. So you can see the difference in the flow levels. There are some differences, but they're reasonably good. No model is perfect, of course, but some models are useful. But it's not just accuracy, it's processing time as well. So UIM, 98 minutes, whereas a ranked model on the same CPU, 7 minutes. On the GPU, 4.2 minutes. It's much, much faster. We've only had a very small loss of accuracy. Another test case, because we do have a variety of test cases. So this is the Environment Agency, the UK Environment Agency, have a set of test cases. So this is the terrain here. And then we have a flow rate which comes from this point. So the Environment Agency have tested a number of models, including UIM, InfoWorks. There's a number of other popular ones on here like JFlow, or JDA, or ListFlow, Michael. As you can see, none of the models perfectly agree. So which model is right? Unfortunately, this was the weighted model in version 1, as I was saying earlier. That's not too great. I mean, those are small differences, but that's not great. So we have to address this problem. So this is a special case, this test case, is in floodplain populations where the weighted rule will suffer because it is holding back that little bit of water to try and avoid the oscillations. This limits the accuracy. So the solution was to, instead of just using the water depth of the smallest cell, we used the Manning formula, but only on one neighbourhood, so we're not using it 4 times per cell. We used the Manning formula. We've actually simplified the Manning formula from a cube root to a square root. This is only applied to the largest neighbour. So we use the Manning's formula to calculate the total amount that will move, and then again we use the simple meeting system to distribute that water amongst the cells. Show you some processing time differences. So the weighted rule is a little bit slower. No, it's much faster on the same CPU. So 2 minutes, you had 7 minutes. Even faster on the GPU. And there's a very small difference in quality, but a very large difference in processing time. So we consider that an acceptable loss. Another Environment Agency test case. You can see see the contours of the train here. So we have a number of depressions. And this little red line up here is where the dam break occurs. So we set the water level to this level. And then as flow is removed from those cells into the drain, we set the water level back up to that level. So in this one, you can see we are doing quite well. There are some other rule sets which are not done quite so well. This is the 0.4, so that's the top left, right near the dam break. Another point. We are doing much better than both these rule sets. Generally, we agree with most of them. There is quite a wide variation between most of the models on this one, but we are probably within them, I would say, up from the outline models there. So this is the environment test 8A, which is a little bit more realistic. So we have a train that's got roads and buildings in it. And we're going to have both a pluvial event, so rainfall, and we're going to have an inflow, so something like a pipe burst up at this point here. It's actually modeled on an area. Let's go. As you can see, we're doing reasonably well here. There's some disagreement between all of the models. Doing quite well. Yeah. Again, apart from the outlying couple of models here, we are doing quite well. Now the environment test 4 with the weighted model version 2, so we did a bit better this time. I say that again. I mean, it's obviously some disagreement with the developed models, but of course we need to consider processing time. So if we compare that to the version 1, which was quite a bit of a way out. Again, there are some differences. There are some differences between all the models. Which model is best? Is a question. So the Environment Agency have tested these other models that have runtimes for them, so we can see how our runtimes compared to most of their tests. Of course, we are reasonably equipped model as well as being quite accurate. So a real test case this time. This is the torquay. So DTM is quite large this time. So we've used several different cell sizes. So we've used 8 meters, 4 meters, and 2 meter cell sizes. So this will increase the number of cells, which will increase the complexity. Given we're using the same machine, it will take quite a bit longer to process. You see the train here. Wisely, they built it down in the valley. Seems to be the way. So a number of metrics that we're carrying out on differences. The maximum, the error or the root in the square error, the R2 metric. Let's look at the differences between InfoWorks. It's as close to 8 meters as we can get because it is in a regular mesh. It's not always going to be 8 meters, but as close and consistent as we can get compared to the 8 meter weighted model. And this shows the difference. Some differences. There are always going to be some difference between different models, otherwise it would be the same model. Let's look at some actual statistics. Next on there. So again, we're reasonably accurate. I hope this has convinced you that the model is amongst the good ones. Of course, there is the processing time as well. And we are not quicker than 2 minutes to maybe 2 minutes. We use a lot less memory than EPSRC as well. Now what you can do with you can do a lot once you've got that data out. You might want to put it into a GIS system. You could then use that to make a video like I did earlier. You could take the time intervals and animate those together. What I've done here is I've used a system called GDAL, which is Geospatial Database Abstraction Library. So it's basically a system that handling and converting these file types. I've used it to rasterize, to polygonize the raster. So we've turned it from a raster into a polygon. We've then put it into Google Earth, but you might put it into some other 3D visualization. And now these people are talking about it. So let's show you what this looks like. So this is another pipe burst. Technical difficulties. Let's go find that. Yeah, I think I might have to play that for you a bit later. That will work. Sheffield United just another building. This is an artificial test case, which in effect there should be insurance. So you can zoom down and ask, why is that roundabout so flooded so deeply? There's a subway there. So there is some depression. While you're watching that, I'm going to grab the power supply. Battery plugged in. Pretty, isn't it? Yeah. So not all PCs though will have a good GPU. Basically, laptops are not big enough to have a good GPU in there, as good as we like. So what we've done for this workshop is we have set up a cloud computer. This has a rather powerful P100 Tesla GPU. This is the most modern GPU. I have an IP address for it here, so we will connect that to that one. It's located in Shanghai, so we should touch with the connection time and speed. So what I'll need to do is set up a user for anybody who wants to use this. So after this, if you could come to me with a list of people and I can set up the users for you. Then you can use a remote desktop connection. You can simply put in that IP address, your username. You need to set this local resources drivers put there, and then you can share data with it. Connect, put in your password, and you'll be connected to a Windows system. After that, you need to bring up a terminal or a command prompt. So press the Windows button, type in CMD for command, press enter, and you will get a command prompt. You then need to change the directory to where I have put the application. So CD for change directory. Processing, trying to make that short. And then, as I said earlier, you run the application, try and get the input file and location, and the output location. And all the settings are in the office at that time. So once it's running, you'll see this lot of information very below that. So it will tell you where in simulation time it is. So that's 50 minutes through the simulation. And the actual processing time it's taken so far, so it's done 50 minutes worth of simulation in 40 seconds. A bit of information about how the adaptive time step is working. The average time step, number of iterations, upstream elevations, and the maximum flows that it's getting at the moment. And then whether you've had a rain, this one's had some inflow. And at the end of the simulation, it will tell you the total processing time. So this is E81, and then it will tell you where it's put your output files and what it's named them. So it's used that short name to help identify it, and then the name of the setup file, you identify this. Or whether it's the maximums or the time. That is effectively CADDIES in a nutshell. So, open the floor to any questions.
Once the simulation is finished, what do you suggest? Review the ASCII file?
I would suggest something like QIS, which is where you download it. You can just use a text editor as well to look at it.
Yeah, it's pretty.
We do have these systems to change it into a 3D animation that's not fully automated. So hopefully some of the ideas for how to use these will. We've got this cloud computer set up for this week, so if anybody wants to run some simulations, set them up to run for the test cases. Any other questions?
So you said ICM was cheating.
Yes, yes.
You're not simulating hydraulics really, are you? You cheating in the hydraulics. And then a misleading level of accuracy associated with that. So you're both cheating, would you suggest?
I did admit we've lost some of the accuracy, but I hopefully tried to show you that we are reasonably similar compared to the time difference in processing. So it's only a very small difference in accuracy.
If you were running in single point, do you still sit within the rest of the simulation engines?
So there'd be very little difference to.
It's twice as fast.
There'd be a little difference in accuracy, of course, but that would be down to the precision level.
Yeah.
Obviously, ICM would be but generally we all use double floating point precision for these models. But we would go twice as quick as we go right now. So that would be the main advantage. Does that answer your question?
The question was, if you go to single precision,
yeah,
do you still sit within the rest of the simulation engines in terms of the test cases?
To be honest.
Because if you do, you might as well
just carry oranges and apples unless they use single precision as well.
Not really, because you only care about the output, right? You only care about
output and the processing speed. But yes, yeah. Perhaps there's something to compare with the future. There's the trade-off then. That's what we're looking at, basically the trade-off between accuracy and processing time. Anybody else?
Just a question. Are there example cases on the GPU to practice with?
Yes.
No.
So they are on there with the setup files, so there's quite a few that you can go through.
Do you see the run from the root and how a cell is taken up by the building only maybe 50%? How do you consider this?
Okay. So it depends on how you make, first it depends on how you make that mask. The mask is a raster. So once you convert your polygons from the building into a raster, that's the point at which you decide whether a cell is inside or outside the building. So it depends on your polygonization algorithm. And the other part of it, it depends on how you set the building. Are you going to set it to 20 centimeters or are you going to set it to 3 meters? In either way, the building is a surface that water can be on. So if you've got it at 3 meters, it's kind of on the roof and can flow off the roof. Does that answer your question? Or?
And where can I download the benchmark test?
So you should be able to find most of them on the internet, or I've got the setup files for them on the cloud computer.
Okay.
It's next from that agenda. What am I doing for time? So I think we'll take a break at this point to let that simmer in mind. Right.